Hi everyone, this is your math guru. In this video, I'm going to show you how to solve the following quadratic and linear function questions. Please don't forget to click on the like and subscribe button below for more easy to understand math concepts. The first question says, a line has an equation of y equals 3x plus k and a curve has equation y equals x squared plus kx plus 6, where k is a constant. Find the set of values of k for which the line and curve have two distinct points of intersection. To start with, when two lines intersect, if a line AB and a line CD, I'm going to tag them appropriately. This is line AB and this is line CD. At the point where they intersect or where they meet, the coordinates of that point for the two equations are the same. So the coordinates at this point will be the same for the line CD and the line AB. So going back to the question, we've been told that we should find the set of values of k for which the line and curve have two distinct points of intersection. And what that means is, at that point, the equations of those lines are the same, both the curve and the straight line. So starting with the equation of the straight line, I have that to be y equals 3x plus k, and the equation of the curve is y equals x squared plus kx plus 6. So like I stated earlier, because the 2 points intersect and we're trying to look for the value of k that makes that statement true, then we're going to equate the two equations together. So that means equation 3x plus k is equal to equation x squared plus kx plus 6, which is the point of intersection. Moving all values to one side, I have x squared plus kx plus 6. If I move my 3x plus k, it will become minus 3x minus k, all equal to 0. Collecting like terms in x squared, I have that as x squared, and terms in x, I have that as plus kx minus 3x. Then I have my constant term plus 6 minus k, all equal to 0. So what I've done is to write it in a quadratic form, that is ax squared plus bx plus c is equal to 0. In order to get the values of a, b, and c, I'm going to factorize the terms in x such that I have x squared, which makes my a1, plus, if I factorize out x, the coefficient of x will be k minus 3, plus, then I have my constant 6 minus k. That means terms that doesn't have or are not attached to the variable x. A in this case will be 1. That's if I equate it to the quadratic equation. My b is equal to k minus 3, and my constant c equals to 6 minus k. Note that we are trying to look for the set of values of k for which the line and curve have two distinct points of intersection. So what that means is my discriminant, or my delta, must be greater than 0. If my delta is greater than 0, that means I have real values such that my delta is equal to b squared minus 4ac. So substituting the value of b squared minus 4ac, which must be greater than 0, what I have is, I have my b squared. B in this case is k minus 3, so I have k minus 3 all squared minus 4 times my a is 1 times my c is 6 minus k, close bracket. The value of my discriminant must be greater than 0. If I expand the brackets, k minus 3 all squared will give me k squared minus 6k plus 9 and minus 4ac, that's minus 4 in brackets 6 minus k. If I expand that also, I would have minus 24, that's 4 times 6. Then minus 4 times minus k, that's plus 4k, all greater than 0. Collecting like terms, I have that as k squared minus, I have 6k plus 4k. I'm going to adjust that. So minus 6k plus 4k will give me minus 2k. Then I have 9 minus 24 minus 15 is greater than 0. If I factorize my left hand side, what I have is k minus 5 and k plus 5. I need to test my points on the number line. Now it's k plus 3. I'm going to correct that. So testing my point on the number line, I know that k will have values of 5 or minus 3. So I have minus 3 and positive 5. It's important to test your position because that will determine the equality sign to use. And I got my minus 3 and 5 values from k minus 5, that will be greater than 0. That's k is greater than 5, or k plus 3, which will make k negative 3. So if I go back to testing my point, I'm going to pick points before negative 3 or greater less than negative 3. I'm going to pick a point in between negative 3 and 5, and I'm going to pick a point greater than 5. Let me start by point less than negative 3. If I pick a point, let's say minus 4, if I slot in minus 4 back into my equation, what I'm going to have is minus 4 minus 5, that will give me a negative value, times minus 4 plus 3, that will also give me a negative value, and negative times negative will be positive, which is a value greater than 0. So at this point, I have points greater or less than minus 3 fulfilling the condition. Then I go back to testing the point between minus 3 and 5. If I test the point minus 2, for example, minus 2, if I go back to the equation, the inequality, I have negative 2, negative 5, that will give me a negative value, minus 2 plus 3, that will give me a positive value, and if I multiply minus and plus, it will give me a negative value, which is not greater than 0, or which does not fulfill the condition. So what that means is points in between negative 3 and 5 will not make that inequality positive or fulfill the condition. The last point I'm going to test is a point greater than 5. So if I pick 6, for example, which is a value greater than 5, and I go back to my inequality, 6 minus 5 will give me a positive value, and 6 plus 3 will also give me a positive value. Positive times positive will give me a value greater than 0. So that means at this point, I have the condition fulfilled. So therefore, the values I'm looking for are k must be less than negative 3. I'm going to show you that on the number line. So I have values greater than 5, and I have values less than negative 3. So I have k less than negative 3 and also k greater than 5. So for this 2 point, I'm going to have the set of values of k for which the line and the curve have 2 distinct points of intersection. Let's look at another example. In my second example, I have a curve's equation y equals x squared plus 2cx plus 4, and a straight line has the equation y equals 4x plus c, where c is a constant. Find the set of values of c for which the curve and line intersect at 2 distinct points. Like I mentioned earlier, at the point of intersection, the 2 equations will have the same coordinates. So therefore, my first equation, y equals x squared plus 2cx plus 4 will be equal to my second equation, that's 4x plus c. So equating this two together, I have x squared plus 2cx plus 4 must be equal to 4x plus c at the point of intersection. Moving all the terms to one side, I want to rewrite it as a quadratic equation. I have 2cx plus 4, that'll be minus 4x minus c equals to 0. Collecting like terms, I have that as x squared plus 2cx. I'm moving all the x coordinates or terms that have x as their variable to one side altogether. So I have minus 4x plus 4 minus c equals to 0. I have x squared plus terms in x that have coefficient of x, that's 2c minus 4 plus, and then I have my constant term 4 minus c equals to 0. Like I mentioned earlier, to have real values, that means my discriminant delta will be greater than 0, and we know that delta is equal to b squared minus 4ac. So if I go back to my quadratic equation, I have my a equals to 1, which is the coefficient of x squared. I have my b equals to 2c minus 4, which is the coefficient of x, and I have my c equals 4 minus c. So slotting in my parameters, I have b squared, that will be 2c minus 4 all squared, minus 4ac, that's 4 times 1 times c, c in this case is 4 minus c, must be greater than 0. If I expand and collect like terms, what I have is 4c squared minus 16c plus 16. If I expand my right hand side, I have minus 16, that's 4 times 4. Then minus 4 times minus c will give me plus 4c. All this must be greater than 0. So regrouping, I have 4c squared. Then I have terms with coefficient of c. I have plus c in bracket. I have minus 16 plus 4. Or better still, I'm just going to add. So I have minus 16c plus 4c. That will give me minus 12c. Then I have plus 16 minus 16. This cancels out. I still have my greater than 0. And if I factorize, I have that as 4c in bracket, c minus 3 greater than 0. So like I did in the last example, I'm going to test all my points. If I have my number line, I have point 0 and point 3. I got that from 4c equals to 0, that's c is 0, or c minus 3 equals to 0, then c is positive 3. So I need to test the 3 point as shown, points 1, 2, and 3. That will make the inequality true. So points before 0, if I have negative 1, which is less than 0, and I put it back in my inequality, so I am going to have a negative value, because negative 0 times 4 will give me a negative value. So I have negative times, then if I have negative 1 in my bracket, negative 1, negative 3 will also give me a negative value, and negative times negative is positive, which is a value greater than 0. So at the point less than 0, I have that to be true. In between 0 and 3, if I use the point 2, for example, before For C will give me a positive value, so because 4 times 2 is positive 8. Then if I test my bracket, 2 minus 3 will give me a negative value, and positive times negative will be negative, which is a point less than 0. So in between 0 and 3, that doesn't make my inequality true. The last point is a point after 3. If I, for example, I test 4, what I'm going to have is 4, positive 4 times 4 will give me a positive value. So I have that as positive, times 4 minus 3 is also positive. That's any value greater than 3 will give me a positive value. And positive times positive is greater than 0 because it's going to give me a positive number. So I have that point true. So if I redraw my graph or my line graph, what I'm going to have is point less than 0 makes the inequality true, and points greater than 3 makes the inequality true. So the value of C will be less than 0 or C greater than positive 3. Thanks for watching. Bye.